All right. So when it comes to columns, most if you look at four main end conditions, right? Well, it could be any of these four here, right? So let's name them one, two, three, and four, right? Could be any of these four. Well, in the first condition or in the first one, we have one end fixed and the other end free. You can see how everything is written already. Right? The effective length is saying that after the load is applied, the effective length of the whole beam. That's what we mean by the effective length. So though the length is L, because of the loading conditions and the end conditions and everything, for example, for condition one here, the effective length ends up being twice the length, right? So for each and every one of this, there has its own effective length, right? The other thing is that when we look at these particular four diagrams here, one thing is that you see that the loads, right, especially the P's, right, the P's actually uh, were initially in line, or they are in line, or they are initially in line with the, what do you call it, the central axis of the beam, right? So this P here was actually here, right? But as it continues to act on the, what do you call it, the column shift to this side, right? But it still ends up acting just at the center, the central axis of the beam, right? That's the thing. We look at the example 2, for instance, still the same thing, acts at the center, which is where we have that violet or purple line. The same thing here, same thing here, right? Then for these ones, this is where the loading is at the central axis of the beam, right? But then we have a special condition where the load is not at the center of the beam. This is what we call eccentric loading, right? And then this is where we have, so the reason why we end up, let's go over this one more time. The reason why we draw the what do you call it, the beams here to be one line, as we see in the red ones, right? Is that the assumption is that there's no need to go within the fiber of the beam, and then the loads, right, are actually at the central axis of the beam, right? Then the special case. The special case is that the loading is not at the center of the beam, the central axis of the beam, right? So this is the case that we have here. So let's this is our 5, right? Now we are here. The load, which is P, is not it's a line of force, is this yellow line here, is not at the center, which is this violet line here, or the purple line, what do you call it? Dashed line, right? Is not at the central axis of the beam, right? This is what we see as eccentric loading, right? And for this particular condition, there's a particular way that we check the, what do you call it, the maximum stress, and then we check the deflection within the beam, right? But then the end conditions remain the same, right? The end conditions remain the same. Just that when you look at a particular eccentric loading, you must look at the appropriate, what's the name, effective length, and then know how to find the deflection and then the stress. So for the eccentric loading, there are particular equations that help us to find the deflection and the maximum deflection and the maximum stress within the beam, right? Everything has been done already, right? And so whenever you see this sec function somewhere, which we know it to be inverse reciprocal of cos, right? So this right here is this, right? Then we know that we are actually dealing with eccentric loading. So you only use this equation when the loading is eccentric. And then this KL here that we are having is actually the effective length, right? So let's go over that one more time. We know the sec is reciprocal of cos. The KL that we're having here is basically the effective length, right? Because we see that the K is the factor, whether 2 for, what's the name, one end fixed, one end free, one both end hinged or both end pinned, 0.7. We saw that earlier, 0.7 when one end is fixed, one end is hinged, or 0.5, right? Well, when both ends are fixed, right? So that's the KO. So basically the KO is just the effective length, which you saw earlier. The P, now we are just looking at this first equation. Now we are dealing with this one. The P is just the applied stress, the applied load, right? The E is modulus of elasticity. R is what's the name? R is the second moment of inertia. Both of these, at times, these two are not given individually, they are given together, and then there's a name for it, which we call flexural rigidity, right? Flexural, write this up. it's not always that they are, because they are both constant, dependent. E is just a constant, a material constant, but I is a cross-sectional constant, like depends on the geometry of the material. So like EI together when it's given, if you don't see them individually, we say flexural rigidity. Yeah, so this is the name we give to these two, and then one. And then the reason why these two equations are the same is that we'll go through it very fast. I still want the maximum deflection, right? The reason why we say this and then this are the same is that this how we go. The only difference, so let's see. The main difference between these two, and the reason why they are slightly different, is just the P that I've introduced, this critical load that I've introduced, right? So the critical load, right, is basically a pi square EI, right, all on effective length, right, and which we know effective length to be what? K and then L, right? So let's put that there. So let's take this LE away. So then you have this KL here. So as a matter of fact, if you go through it and then you put everything there, you see that you actually end up turning this equation here when you put the critical load into this one. So that's it. And since Y max, or deflection maximum, is what do you call it? Just a distance something, then you need to be just a distance unit. Mm, we have M, just that. And anything that's just the same, has the same what do you call it, unit as distance, right? And now we have the stress, right? The maximum stress, just the same thing. These two are the same equation, used to represent the same thing, but in different scenarios. Okay, so let's see. I'll go over the terms in the constant and everything. So P, the load applied, cross-sectional area, right? E here, so let's go up. E is the distance between the load, right? The load of the line, and then the central axis of the, what do you call it, the beam, right? Which we call the E, or the eccentricity. If E is not said, eccentricity, right? So that's the E. The C is the distance, the C here, this C here is the distance from the central axis. So let's see, from the central axis to the outermost fiber, right? So from here to here, that gives us our C, right? And then what do we have again? Let's see. C. And now we have a new term we've seen to be R. This R here, the R is a combination of two, it's what do you call it? Depends on two, what do you call it? Sectional properties, right? So the R here is a square root of the cross-sectional area all over the, what's the name? The schematic of inertia of the beam, right? So this R, if you don't see it directly, you can, if you can find this and this, then you can find the R, right? And then we see the R is the radius of gyration, right? Now we know what the sec is. We already know what the sec is. We said the sec is the reciprocal of cos, so 1 of cos. Whatever it is that you have here is the inside, right? So sec is reciprocal of cos. Now what are we looking at? We know the KL already, so let's a minute. We know that the KL is the effective length, and then this 2R here, just 2 and the radius of gyration, EI, and this that, what do you call it, the applied load, right? The same E here, eccentricity. This is the distance from the outermost fiber to the central axis, radius of gyration, reciprocal of course. And then we'll try to, what do you call it, use this where we have critical load is equal to pi squared flexural rigidity, which is EI on KL. When you put it into this here, if you try to, basically this one is with this that we end up with this one. So like it's actually they are the other way around. So the general one is this, and then we turn it to this one, right? Because we put the values, what do you call it? We put everything that we have for PCR in, and we get the one up here, right? The same thing for this. Put everything I have for PCR, and then we get this one up here, right? So since it's stress, either Pascal, the unit should either be Pascal. We should be very mindful of the unit, or Newton per meter squared, right? Force per unit area, right? Or Newton per millimeter squared, or Newton per meter squared. Yeah. So that's it.